We're back. So we have learned how to derive the moment of inertia for a simple shape, for a solid cylinder. And I will try to use that terminology. I'll try to talk about solid cylinders rather than discs or other shapes. I'll try to talk about hollow hoops, and I'll talk about solid spheres so that you get used to that terminology. I don't want you to not get one of these things right because I use a term that you're not familiar with. But a compact disc would be basically it would be a solid cylinder. You'd ignore the hole in the middle. A length of pipe would be a hollow hoop, if you like that. So we've learned, we've been given the three examples, the three numerical values, and we learned how to derive the solid cylinder. Now that is in each case about an axis of symmetry. So for the solid cylinder, it's about that axis there, and for the hollow hoop, or if you like the piece of pipe, it's about the axis that would pass through the middle of it, and for the sphere, you know, for the nice sphere, it's like an axis going through the middle of it. In each case, it goes through the middle. And if I chose to take my axis through there, or my axis through there, then it would not be the same. You know, if I chose to do my axis through there, it would not be the same. This is specifically for the axis through what we call the circular center. It turns out, well, in the circle, in the sphere, if I took it like a section, not through the middle, but not through a diameter, but through a section of it, it would not be the same. So what happens if I want to do something that's not through the circular center? What goes on? And for this, I have a thing called the parallel axis theorem, which again is not justified. It's just started. And what it says is, look, if you know the moment of inertia for rotation about the center of mass, and you give me the geometry of how your point of interest relates to the center of mass, I can figure out what the moment of inertia will be about this new point. So, all right, I know it about the center of mass. I want to know it about here. This is how you link the two. The center of mass about your particular point of interest is equal to the center of mass about your, the moment of inertia about your point of interest is equal to the moment of inertia about your center of mass plus, and it's going to be m times d squared, where m is the mass of the entire object, and d is the distance, the linear distance between the center of mass and the point of interest. Now, let's say you can't remember. Think about it. What are the units for moment of inertia? What are the units for moment of inertia? Kilograms, meters squared. So if equations involve equivalencies, the units on the left must equal the units on the right, because there's an equal sign there, and each term on the right has to have the same units. You can't add apples and rockets. It makes no sense. So if this is in kilograms meters squared, this must be in kilograms meters squared, and that means that this must be in kilograms meters squared. So what's your best guess? Well, something that's measured in kilograms and something that's measured in meters and square it. I mean, it's like, you know, all you got to remember is there's no wacky fraction in front of it. It's not 0.72 times this. It's not a half times this. It's just the mass times the distance squared. So, and this is what I see. I see people, and I was just the same, tending to treat equations as magic formulas with no logic behind them. It's just like, you know, like a secret handshake. And if you do it just right, you get the right answer and you get the points. Whereas they're really quite logical. And if you can't remember something, you can at least write down something that could not possibly be right. And that's where your dimensions or your units come in. You at least don't write down something that cannot possibly be right. You don't turn around and say, oh, well, I can't remember, is it m times d squared or d times m squared? Well, it can't be d times n squared because the units are all wrong. So don't make those kind of mistakes with this thing. Yep. So a body has a 4 kilogram body has a moment of inertia about its center of mass at 6 kilogram meters per squared. What is the moment of inertia of the body about another axis that is located 2 meters from the center of mass? Okay. So I'm going to say I, center of mass, is equal to 6 kilograms meters squared. That's that guy. That's my I. And I know that my total mass is equal to 4 kilograms. And I know that my distance between the axis of the center of mass and the axis through the point of interest is going to be, let's have a look, 2 meters. So then I say, well, I through my point of interest is equal to I center of mass plus m times d squared. So I axis of interest is equal to 6 plus 4 times 2 squared. So this is equal to 6 plus 16. So this is equal to 22 kilogram meters squared. Now, everybody see where that comes from? So it's just remembering it, yeah? Just no. Now, let me ask you a question. Can you intuitively tell me, is there any parallel axis to do with this object which would have a moment of inertia which is smaller than the moment of inertia about the center of mass? Can you imagine an axis parallel to the center of mass axis in this potato or outside the potato which has a smaller moment of inertia than this moment of inertia about the center of mass? It's not going to happen, is it? Because you're always going to add on this bit. It's only going to make the thing more sluggish. And if it didn't, then when you threw something through the air, it would rotate about that other axis. But when you throw things through the air, they rotate about their center of mass because that is the axis which has the lowest moment of inertia. Things rotate about the axis that's easiest to rotate about. So if we remember that we always rotate about our center of mass, that means that it must be the lowest moment of inertia associated with the axis through the center of mass. Cool? So bring in your conceptual physics. Okay, so we've kind of introduced and we've talked about the moment of inertia. Now let's go to the next level and use it. So we had this thing called linear kinetic energy, and we said, well, okay, kinetic energy equals a half mv squared, so kinetic energy of rotation equals a half I omega squared. Whoa, 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 whoa. This means that there is kinetic energy stored in my object because I'm rotating. This means there's kinetic energy stored in my object because I'm translating. I'm moving through space. Yeah, I'm used to that, half mv squared. But if I roll through space, then I also have kinetic energy locked away because I'm rolling, because I'm rotating. So that raises some interesting issues. A system consists of a body having a moment of inertia of 5 kilogram meters squared, which rotates at 3 radians per second about its turning axis. What is its rotational kinetic energy? So here's my system. I know that my I is equal to 5 kilograms meters squared. And I know it's rotating, so omega is equal to 3 radians per second. And I want to know Ke rot. So my Ke rot is equal to a half, not m but I, not v squared but omega squared. So Ke rot is equal to 1/2 times 5 times 3 squared, which equals 3 3s are 9, 5 9s are 45, half of 45 is 22.5. What would the units be? Joules. So it's simple enough. Yeah?
So it's still measured in joules?
It's still energy, yeah. It's still measured in joules. So, this raises an interesting issue. If you're rolling along, not just spinning, you get kinetic energy in that last object because it was spinning. But now imagine you're rolling along, so you are translating while you are spinning. There's actually two ways of analyzing it. The one way is you say there are two components of my motion. There's a translational component and there's an angular component. And therefore there's two components of my kinetic energy. There's a translational component and an angular component. And I'm sorry, on these PDFs, the omegas didn't print, so that's an omega squared.
We have that on
So it's just on mine then. Okay. So that's one way, and it's perfectly good. The other way is you say, I'm going to imagine that this is only a rotational motion. You see here, on the previous way, I'm saying my center of mass translates and my object rotates about the center of mass. Whereas here I'm going to turn around and say this thing just rotates not about the center of mass, but about a point on the circumference. And as I roll down, the point changes. Yeah, I have a different point, but I've always got this thing above it. So I can get the same answer using those two techniques, because in this case, this moment of inertia is not the same as that moment of inertia, because it's about a different axis. Agreed? I prefer the first way. I find it makes more sense to me, and so that's the way I tend to do these things. A cylinder of 4 kilograms, 3 meters radius, rolls along a surface with a translational velocity of 6 meters per second. What is its total, there's the giveaway, total kinetic energy? So here's my cylinder. 4 kilogram, 3 meters radius. Translational velocity. What is its total KE? So my KE total is equal to my KE trans plus my KE rot.
Is that VC equals?
VT.
No.
So KE total is equal to 1/2 mv squared plus 1/2 I omega squared. Okay. What is my mass? M is equal to 4 kilograms. What is my V? V tangential, translational, is equal to 6 meters per second. What is my I? Ooh, I don't know it. But I do know that it's equal to, because this is a cylinder, a solid cylinder, is equal to 1/2 mr squared, which equals 1/2 times 4 times 3 squared, which equals 18 kilogram meters squared. And what is my omega? I don't know, but I know my omega, remember angular, equals Vt over R. I'm sorry?
Got the K in kilograms for the mass.
Yeah, thanks. Thank you, yeah. So, Vt over R. Now, conceptual issue. V tangential V trans. Up here, when I'm talking about this is V trans. Here, when I'm talking about my omega, this is V tangential.
So you're using the V tangential on both sides?
What's both
I'm
sides?
sorry, just keep going, I got it.
Okay, so the question I got for you is the translational velocity bigger than, equal to, or less than the tangential velocity?
What's that? What's it divided by R?
Just let me finish this question.
Wouldn't it be equal?
So let's well, I'm asking you for bigger, less, I don't care about the sign, just bigger, less than, or equal to. If you think it's bigger, if you think V tran is bigger than V tan, then go A. If you think V tran is equal to V tangential, go B. And if you think V tran is less than V tang, go C. Let's see what we get. Let's do it real quick because I'm running out of time. So
What's the V trans over Y? Or the W?
So what do you think? I'm going to give it just a little bit of time. So I'm comparing the speed with which the object moves across the table with the speed with which a point on the object moves along the tangent, you know, the actual outside edge speed. I'm going to stop it now. So I'm just curious as to what people say. Ooh, mainly B. A few people saying A. It turns out the answer is B. And the only way I could prove this to myself was I got some kitchen towel. And basically I pulled 3 sheets in 1 second. And I said, that's my tangential speed, 3 sheets a second. And then I put it down on the table and I held it with my finger and I pushed it that way, 3 sheets in 1 second. And so the distance traveled was 3 sheets in 1 second, and the distance unrolled was 3 sheets in 1 second, which means it's the same velocity. So it turns out that these guys are equal to each other. So it turns out that, oh, that means that this omega is equal to 6/3, which equals 2 radians per second. So then I shove this over here and I say my KE total is equal to 1/2 times 4 times 6 squared plus 1/2 times 18 times 2 squared, which equals 3672 plus 2 squared is 4, so that's going to be 4, 2, 36, which equals 108 joules. Okay? So next, we make it that little bit more interesting. And what I do is I put you at the top of a ramp. And I say, okay, roll down. I want to know the speed at the bottom of the ramp. So this is 2 meters radius. This is 30 meters up there. And it's 4 kilograms. At the top, I hold it before I let it go. At the top, what kind of energy has it got? Gravitational potential energy. At the bottom, what kind of energy has it got? Be more specific. Is it sliding or is it rolling? It's rolling. So it has two forms of kinetic energy. It is translating and it is rolling. If it slid down, it would only have translational. Because it's rolling, it's got both. So we say ME top is equal to ME bottom,
What's
mechanical energy. So I say mg times h is equal to 1/2 mv squared plus 1/2 I omega squared. mgh is equal to 1/2 mv squared. Let's leave it in letters. What is the equation for the moment of inertia of a hollow hoop rotating about its cylindrical center? Mr squared. And then what is the equation for the angular velocity in terms of tangential velocity? Remember, angular omega r is equal to vt. So v omega is equal to vt over r. So vt over r squared. And then remember that this v translational and this v tangential are the same thing. So mgh, so v tang equals v tran. Let's call this tran. Equals 1/2 mv squared plus 1/2 big M, oh no, same M, r squared v squared over, is this r here the same as that r there?
No.
Why are they different?
Because that's the little r, that's the big r.
Isn't this the tangential velocity at the edge of this thing? And isn't it the radius of this thing?
Sure.
And isn't this the and isn't that the radius of this thing? So aren't they the same?
Yeah.
Good. I knew you'd come around in the end. Okay. So then mgh is equal to 1/2 mv squared plus 1/2 mv squared, which equals mv squared. Because it's two halves added together. So gh is equal to v squared. So v is equal to the square root of gh. So this is going to be the square root of g's 10, h is 30, square root of 300. V is equal to 17.3. This is a classic test question.
So I have no idea what you just did.
Well, you just look over it. That's why we got the video, so you can see it. So we said that our energy at the top equals the energy at the bottom, and we defined our energy in terms of the different components. And then we put equations in for those different components, and then we recognize some similarities. My velocity of translation is the same as my tangential velocity, so I can just represent that by v. And I recognize that my radius in my moment of inertia is the same as the radius in my conversion from angular to tangential. Then I cancelled where I could, simplified, and then I shoved my numbers in. Question? So when you say negative, square root of a value can be positive or negative, yeah? So yeah, you could put negative down, but I'm asking you for speed, and isn't speed always positive because it's a magnitude? Yeah.
So but you said find like the final velocity or something, then we would have to put the negative.
I don't know, because it depends on your axes. Now I'm getting real picky, but it depends on your axes. But I would be happy if you put the negative down. I would be fine with that. But you're saying it's negative because it's pointing downwards.
Yeah.
And yeah, it is, but it's also going to the right, so then how do you define your axis? That's what I'm getting. Good. Okay. Oh, lab. You're going to enjoy this lab.